Hello guys, so welcome back to our VHDL lessons, and we're gonna continue our journey with combinational circuits. And our third example here is the 4-bit binary adder, which is a circuit that adds two binary numbers together. And in that case, it's a 4-bit. It's really important to define how many bits for each number. And in that case, it's really simple case, just 4 bits. Okay. So as we explored in our lectures, on logic design, we can do that using the full adder. Okay, so the general case when you add two binary numbers together is that you will have 3 bits of addition, and we can perform the 3-bit addition using the full adder. Okay, so we're gonna instantiate four others here, and here you have the propagation of the carry from each stage to the next stage, as we learn it in the lectures. So for example, stage 1 here uses C1, which is basically the output or came from the stage 0 or full adder 0. Then full adder 2 will use C2, which is the output of full adder 1, and so on. And finally, the carry of the final stage, C4, is basically the carry of the overall circuit. So the circuit basically has 8 inputs, which is basically these 8 inputs, A0 to A3, which is basically the first binary number, and then B0 to B3, which is basically the representation or the bits of the second binary number, because it's 4-bit. Then we have 5 outputs. From the sum is 4 bits, and the carry is the 5th bit. And remember, the addition, is really, the output is connected. The final number is, when you represent the final number, you need 5 bits. So you're gonna, if you wanna, for example, to convert this result into to decimal, to read it and know how it is as a number, then you must convert the 5 bits together. Okay. Okay, so let's do that. So to do that, we need to instantiate a package out of our full adder circuit. So we explored the 2 of them. One was optimized, and one was very fast to design, but not optimized. So I'm gonna create a package out of the optimized one. Okay, and here is the optimized adder, in which we replaced the third half adder of the first design with just an OR gate like this. Okay, so here we create a package like this. It's really simple one. Okay, I just name it full adder version 1 package. And the component is the name of the entity that we have here, exactly the same, copy and paste. And here again, copy and paste of the, the entity of the design. Then we should, create a library if we don't have, and create a folder for it on our PC. Please, review our previous videos for that. Then finally, we should add this component to it. But first, we should compile. So compile first, so compile all. Maybe we have some errors because I instantiated new designs, maybe. So this is full adder, let's check here what we have. So full adder v1 package doesn't, so let's check that. Full adder v1 package. Yes, so here is this name here. I'm sorry, this name here should be also here. Okay, so I'm sorry, this name here should be also here. Okay, so let's now compile, because basically I'm doing copy and paste. Again, use what we have. You don't need to write everything from scratch. Those should work. Yeah, that's good. And it's good to also to see or explore possible problems or bugs in your code. Okay. Good. We have now a package called full adder v1 package. So let's check our library here, digital component, full adder. This is a previous one that I did, and this is a new one. So where it is, it doesn't. Yeah, because we just compiled. We didn't add it, so we just added first. So here is a command that do that for us. That's good also, another. So good. Now it's added. Look, a full adder v1 package. It's really good to, explore with you possible problems that you may have. So we must compile, and the compile must be successful, and we must add it, using that command here. Okay, now we have this as a package. Now we can do our 4 binary other circuit or design. So here it is, okay, and I did it in 2 ways, as we will explore. One is really simple to understand, and then we're gonna discover some problem, tiny problem with it. Then we explore another one, which is basically the commented code here. Okay, so let's see. This design has 2 inputs or 8. Okay, it has 8 bits as inputs, but remember, these 8 bits are just 2 things, 2 binary numbers. Each one is 4 bits. So the way to define, a variable, a Boolean variable in VHDL that has many bits is that way. So all the time we explore, or we use standard logic, which define 1 wire, 1 bit, But now, if you have a number that is more than 1 bit, we use standard logic vector, okay? And 3 down to 0 means, bit 3, then bit 2, then bit 1, then bit 0. You can do both. You can say 0 up to 3 or 3 down to 0. But what you used, you should stick to. That's very important, okay? So we have 2 inputs. Let's call them X and Y, or A and B, whatever you call them. Okay, so I named here A and B. I called them X and Y. That's fine. Then our output is also 2 things. So we have the sum, which is 4 bits, 3 down to 0 again. And we have our carry, which is just 1 bit. So here we use the standard logic. So the take here is that if you have a variable that is more than 1 bit, use the standard logic vector. Good. Now we define, the architecture. Basic architecture is structure. Okay, so we should change this, although that's fine. I mean, if you keep the same name, that's fine. And if you change it here, you should also change it here. But that's fine. I mean, this is just a name. But we like always to give good names or descriptive names for our design. This is a structure. This is a structural design, not a behavioral one. Okay, good. Now, if you look here, guys, C1, C2, C3 are all internal, internal signals. Okay, so we will not see them in the output or the inputs. These are just internal signals. So I defined here a signal, and in purpose I also defined this signal as also standard logic vector. You can have 3 signals. You can say, for example, let's do that. You can say signal C1, then C2, then C3. Okay, and that's it. Sorry, that's it. Or you can do it in a modular way and define a vector, and this vector will have in it, each bit will represent one of these carries. Of course, here we have 3, so we don't need 3. We don't need 4 bits, and 3 down to 0 will give you 4 bits. 3, 2, 1, 0. So do it 2 down to 0. Okay, not 3 down to 0. Also, if you make it 3 down to 0, that's fine, because again, you can define whatever number of signals you have. But what really matters here in your design is the signals that you will actually use. So here, if we keep it 3 down to 0, one of the bits will not be used at all. So why you keep it? So just remove it and make it 2 down to 0. Okay, and again, those guys will not be used because we're gonna use, our signal here. And I call this signal rebel carry. Okay, this is also a good name because this is not just the carries. There is a propagate, as we explored or highlighted in our lectures. These carries propagate. Okay. So C1 takes the delay of the first half adder. Then C2 will appear after 2 delays, 2 half adders. Then C3 will appear after 3 days. So there is propagation delay here, or rebelling, we can say. So we can call them, and many use such name, rebel carry. So we have here a rebel carry, okay, that rebels from, like a wave, from one full adder to another full adder. Okay. Good. Now, the easy step, which is instantiating 4 of these full adder. So let's call the first one full adder 0. Full adder 0 will have the first 2 bits of the our inputs. Here, of course, in the in the photo here, it's A and B, or image A and B. Here I'm calling them X and Y. That's fine. So X, its 2 inputs are X 0 and Y of 0. And here is how you choose 1 bit out of a vector. Okay, so X0, Y0. Remember, in our binary adder, the first carry is always 0. So here how you define a signal as a 0, or input as a 0. Okay, these are the 3 inputs of the full adder. Now the outputs will be the carry and the sum. So basically, the full adder 0 will give you one of the outputs, which is S of 0. But remember, here the output is called S. All these signals are called S because it's now a vector, and the output of the first full adder is just S of 0, bit number 0 of the vector S. And the carry, this carry here, okay, will be the first bit of our signal called rebel carry. So this will be rebel carry of 0, which is just an internal signal. Okay, now full adder one, this guy here will have the two bits of X and Y inputs, X of 1 and Y of 1. And the third input will be the carry that was generated from this full adder 0. So this will be rebel carry of 0, which is this bit here. Okay, then the output will be this carry here, rebel carry of 1, the output of full adder 1, and S of 1, this bit of the sum. And you just continue in that way until you reach the final one here, full adder 3, which takes the third bit of fourth bit, of B and A, or X and Y in our case here, because I changed the naming. Okay, then this carry, which is the output carry of the full adder 2, rebel carry of 2. Then the carry, which is basically the overall carry of the circuit, C. And S will be S3, S of 3 here. That's very fine and will work flawlessly with you. Okay? But let's now ask, so this is correct. Again, I'm just confirming on this. This is a very correct design, and it will work for you. But one, observation here. This is 4 bits, so we can just repeat, 4 bits, just copy and paste and make minor changes, and that's it. But if you have a 64-bit binary adder, what are we gonna do in that case? So are we gonna, repeat these 4 lines 64 times and make all such changes? It's really will be a hassle for you. So there is a very, very, very important and convenient, feature of VHDL language, which is the generate, statement. So generate a statement will generate statements for you out from, from nothing. I mean, instead of generating these, so look here, full adder 1, then everything here is 1 except that guy, which is 1 minus 1. Okay, then full adder of 2, again 2, rebel carry of 1, which is 2 minus 1, then 2 again, full adder of 3, rebel carry of 3 minus 1, then the final output, okay, this guy, and S of 3 as well. Okay, so we can make a kind of repetitive, something like for loop, we can say, and this is really a for loop. It's a for generate, okay, in VHDL. So I'm gonna comment all these 4 lines, and I'm gonna use this new statement that is called generate, for loop generate. So I'm gonna uncomment all these lines. Again, the first 4 lines, if you just keep these commented and use those, this is very correct, okay, but not convenient and not a general thing to do. But a general thing to do is something that you can write easily. If you have 64 bits, that will be very hard, okay, and you will have many bugs, because one line that is not corrected or not changed very well according to design will spoil everything. Okay, so the first line here looks like it out of our repetition pattern. So I'm gonna implement it, just as itself, like full other, board map, x of 0, y of 0, then again 0. This is basically what makes it out of the pattern. And rebel carry of 0 and s of 0. And now the statement that called generate. This statement need a label, okay, because you may have many generates, because you may have many patterns in your coding, okay. So basically, for any pattern you have that you want to make using generate, use a different label. Okay, here is for example G1. And then you can say for I in 1 to 3, because here we start from 1 to 3, generate. Okay. One note here, it's really very important about the third or the number 3 here. So number 3 is basically number 2, but the carry here is called C. So you can do that using what I did in the first place. Okay. So basically here, now we should use the third, increase the size of this rebel carry to be 4 bits. And the fourth bit, which is number 3, will be used to generate that line. So that line will be full other 3, for example, full other board map, x of 3, y of 3, rebel carry of 2, which is I minus 1, or 3 minus 1, which is 2. Then rebel carry of 3, then is 3. But how about this guy? Then in another line, you say that C, which is the overall carry output, is equal to rebel carry of 3. Okay, that's really a very good feature in VHDL. So let's go loop by loop, iteration by iteration, and let's examine what we're going to generate out of this line here. So basically with generate, you can just give one label here. You don't need to name many labels. So it's just one label. And I called it full others because this line will generate many full others for us. Okay, 3 exactly. So full other, board map x of 1, y of 1, rebel carry of 1 minus 1, which will be 0. Then rebel carry of I, and I now is 1. So this will be rebel carry of 1. Then s of I and I of 1, this will give us s of 1. So this is, so when I is equal to 1, this line here will give us this line. Also, of course, without the label. So the label here, just don't care. Don't care about it, since you have one label for all of them. And that's here, acceptable with the generate statement. Now, when I is equal to 2, this line should generate this line for us. Let's check. For other board map, x of I, and I now is 2. Then y of 2, because I was equal to 2. Then rebel carry of 2 minus 1, which is rebel carry of 1. Then rebel carry of I, rebel carry of 2, s of I is 2, s of 2. And then finally, when I is equal to 3, again, I of 3, I of x of I, and I 3, so this will be x of 3. Then y of 3, 3 minus 1 is 2. Then rebel carry of 3, okay, so this is a little bit different. Then s of 3. And how to deal with such difference? Just make it another line. So C is equal to rebel carry of 3. That's why in the beginning it was 3. Then I changed it to 2 because I wanted to show you or explain to you this version of the code. Then I bring it back to 3 to show you the most or the best version of this code, because this is a scalable one. If you have more than 4 bits, it will be tedious to do that, and it will be it will be a buggy code. If you have 64 inputs, you must do that in that way. Okay, otherwise you will have many problems. So let's save this guy, compile it. Good. Now let's check the test bench. And the test bench also has some, some changes that makes it really very good test bench. So it's a normal one. Here you have a design that doesn't have any declaration for inputs or outputs, because this is how we use the test bench. We just write it as a complete new design, although it's not. Then here we define the, you know, the entity of the designers that you wanna test, which is basically that guy here. Okay, let's XYSC. That's good. Now here we define signals, just, you know, to represent those guys. So X, N, Y, N, it's out, C out. And again, these are the namings, just namings. You can name it with whatever you want. Then here we instantiate our design. It has four, two inputs and two outputs. And here again, the order is very important. So Xn, this signal will be connected to this X, Yn will be connected to that Y, or that input, S out to S, C out to C. Okay. Now, let's wait a moment here. How many inputs we have? We have two, yes. Each one is 4 bits. So if we count them, if we want to represent all possible inputs, remember each one has each variable is 4-bit. So these 4 bits can be from 0 to 15, right? So we will have, if we just consider them as 8 bits separate, so you will have 2 to the power of 8, which is 2 to the power of 56, variations or combinations. Also, remember the addition operation is interchangeable. I mean, 1 plus 2 is equal to 3, and 2 plus 1 is also equal to 3. Okay, so you don't need to have the 256 because you will have such repetitions, which is not necessary. So you can also again use the generate statement to use what you wanna do. So I'm gonna have here 2 loops, one for Xn and one for Yn, and you must define, you must give them initial values. So Xn will have 4 zeros as initial value, and Yn will have 4 zeros as initial input. Then you wait for 1 second. So this will give you 0 plus 0, which is 0, of course. Then you will have 2 loops. Okay. Remember, you wanna what is you wanna generate here? You wanna say that X is equal to 4 zeros and Y is equal to 4 zeros for 1 nanosecond. Then X is equal to 4 zeros and Y is equal to 0, 0, 0, 1 for another 1 nanosecond. Then X 4 zeros and Y is 0, 0, 1, 0, which is 2 for another 1 nanosecond. And until you reach X is 4 zeros and Y is 4 ones, which is 15. So you want to add 0 to 1, 0 to 2, 0 to 3 until 0 to 15. Then X will be 1. Then you add 1 to 0, 1 to 2, 1 to 3 until, reach 15 and so on. Okay. So you're going to have 2 loops. Okay. The inner loop here, so the outer loop will be for X. So this will add X each time with 1. Okay. Then the inner loop here will be for Y. So for each loop here, we add Y with 1 and we put this statement. Again, generate a statement, or this for loop here, it's just generating, codes for you. Okay, that's it. Okay, guys, one thing here is that we use here the plus. This is the first time we see arithmetic operation. Okay. And for that, we should instantiate that library here. It's called unsigned, standard logic unsigned. So to add a standard logic vector to another standard logic vector, this is basically a standard logic vector, or to perform any arithmetic operation, we define this, this library. It's called the standard logic unsigned, which is basically do addition and subtraction for you. Okay, or 4 standard logic vectors, of course. Okay, so this is basically the design. It's really nice. Let's now compile it. I think this is compiled very well. I mean, it's correct, but let's compile it again. Good. Let's now check the output. And we're going to have another, important observation in the output when we do it. So here our design is full, is rebel carry other, because here again, let's close this for a moment. Here again, the carry is rebelling. It rebels from a stage to a stage, propagate from a stage to stage like a wave. That's why I call it rebel carry order. So let's simulate. Let's go back to the simulation. So our design is called a rebel carry order test bench. So go down a little bit. Rebel carry order test bench. This guy. So okay, and let's have our signals here. Okay. I'm gonna teach you another, important observation here. Look, guys, look at this plus. This means this variable is multiple, more than one bit, as you see here. Look, from 0 to 3, or 3 down to 0. Okay, and again, y is 4 bits, and again our sum is 4 bits. That's why we have it, this button here that you can expand. And we have many, many states in our output. So make it 100, for example. You may have 100, more than 100 combination, basically. So let's, it should be 15 by 15, 225. Okay, because x is 16 by 16, yeah, which is 256 exactly. But you don't, of course, need to change, to check all of them. Okay, just to check, randomly some of these combinations to prove that you are correct. So let's do that now. We have here a lot, but let's. I'm sorry, I shouldn't compile. I should just start here. So let's start. Okay. Now another problem here, we can say. Let's zoom out for a moment here. Is that, again, it's really tedious to have these. So here we have 4 zeros plus 4 zeros. So this is the first bit. 4 zeros for the input, then 4 zeros for the second input y, then the output is 4 zeros. That's good. And then the second, combination is 4 zeros, and then 1, which is 3 zeros and 1, and this will give us 1. Oh, guys, 0, 0, 0, 1. But this is really tedious, because you're gonna convert, because our mind works with a decimal all the time. So it's really tedious to convert binary to numbers, or to decimal. So another trick that you should use here to change the format, to go to format here and use, the radix. Yes, the radix. And it changes the radix from, the global setting is binary, basically, this guy. So change it to decimal, or unsigned decimal, because if you change it to just decimal, it will be signed. I mean, if you have 1 at the most significant bit, it will be counted as minus. So use unsigned here. And look now, after we use, now it's still there. So radix, unsigned. Yeah, this changes only xn. So xn was 4 zeros. Now look, it's just 0. Now let's use it also for y. Change the radix to unsigned. You should change the radix, one by one, or you can choose them all using this way, and it choose, and change all of them at the same time. Okay. Of course, this guy is a carry is just 1 bit, so it doesn't matter, binary or decimal or unsigned. It will be all the time either 0 or 1 in all formats or radices. Okay. So now it's easier to make the addition. So 0 plus 0 will give you 0, and the carry, of course, of 0. Then 0 and 1 will give you 1. 0 and 2 will give you 2. 0 and 3 will give you 3. 0 and 4 will give you 4. 0 and 15 will give you 15. Okay, and again 0, 0 will give you 0. Then 1 and 1 is 2. 1 and 2, 1 and 2. Remember, this is not changing. That's why it's 1 for all 15 nanosecond. So 1 and 1 is 2, or 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5, 6, 7, until we reach here. Yeah. 1 plus 15, this is very important. 1 plus 15 is 16. And remember, 16 is 1 and 4 zeros. Because y, you have 5 bits, 2 to the power of 0, 2 to the power of 1, 2, 3, 5. I'm sorry, 0, 1, 2, 3, 4. I'm sorry, 4. 2 to the power of 4 is 16. So this should give you a carry of 1, and the sum bits should be zeros. And that's what we have here. So 0, and here we have a 1. That's why is 16. And you can just continue such thing, okay, like this. So 2 and 14 is again 16. So 0, and here we have a 1. Then 17. 2 and 15 is 17. 17 is 1 adds a fifth bit to the power of 4, and 1 adds the first bit to the power of 0. So 16 plus 1 will give you 17, and so on, guys. Okay. Maybe you have overflow. Let's check. Overflow, I mean when you add 4 bits to 4 bits, maybe you have overflow. Let's check that. 15 plus 15 is 16, and I think I'm sorry, 30, and 30 is, I think, 5 bits. Let's check. Oh, we didn't reach it, so let's check first here. 6 plus 1 is 7, 6 plus 2 is 8, 6 plus 3 is 9. That's good. Let's run for another 100 nanoseconds. Yeah, we still 12. So 12 is plus 1 is 13, 12 plus 2 is 14, 15. 12 plus 4 is 16, 0 and 1. 12 plus 5 is 17, which is 5 bits, 1, and you have here 1. Okay. Then 12 plus 6 is 18, 1 and 2. 1 here at the fifth bit to the power of 16, plus 2, which is 2 to the power of 1. Okay, so the sum is 2. Let's run for another 100 nano. Also, we don't need all of that. So yes, here it is. So 15 plus 15 is 30. 30 is 2 to the power of 4, which is 16, plus 2 to the power of 3, which is 8. So this will give you 24. Then we need 6. 6 is 1 and 1. So 2 to the power of 2, 2 to the power of 1. So all of them is are ones, except the first bit of the sum should be 0. So let's check that. So here it is. 15 plus 15 is, yes, 1 in the carry, and 3 ones and 0 is just 14. Remember, if you have 4 ones, this is 15. If you remove this one, I'm sorry. If you remove this one, I mean 1, 1, 1, 1, 1, 0, this will be 14. And that's what we have exactly. Okay, guys, that's basically, the binary adder is really interesting circuit because we have many tricks here. We used many tricks or many features of VHDL. First, we used the packaging because we need this package. Then we use the generated statement with for loop, okay? Because again, with for you can just do something like this, like 4 lines. But if you have 64 inputs, you cannot do that. You must have the generated statement that will generate this statement for you. It is just generate codes for you, okay? And finally, in the test bench, again, we have many cases for the inputs. We want to test 0 with 15, 0 is 0 with 0, 0 with 1, 0 with 2 until 15, then 1 with 0, 1 with 1 until again 15, and so on. So you have 225 cases, 225 cases. And of course, you cannot, write all such cases together. So it will take more than, it's around 1,000 line. Okay, so you must again use this for loop here that just generate code for you. Okay, guys, thank you very much for watching this video, and stay tuned for the next video. Bye-bye.